you may be thinking of analytic methods as something that you do on paper and numeric methods as something that you do on the computer. But we're going to be doing both the symbolic and the numeric stuff on the computer. So we can solve systems of equations like the ones that arise from the models that we're setting up, either symbolically or numerically. Symbolically, we're going to be using SymPy. And if you've gone through the introduction to the notebooks, you'll see much the same kind of definitions of symbols and so on. I'm still working through the notebooks and replacing all the big S symbol calls with small s symbol calls. SymPy allows us to define a system of equations as a list of the residuals of the equations. And so when we have something like x plus y equals z, remember the residual is the left-hand side minus the right-hand side. We can then pass this as a list to sympy.solve. I've tried to be quite clear here about kind of which argument is which thing. I would recommend that you do something similar. It does make it a lot easier to understand which thing goes where. You could imagine that I could have worded that slightly differently. I could have made a choice, or the writers of SymPy could have made a choice to say, oh, how you call SymPy is you say, solve for the unknowns given these equations, right? Like it could have been the other way around. Writing out these variable names, it's not necessary. We could have just used exactly that list and pasted it into that position, and exactly this list and pasted it into that position. The result is equivalent, but I like self-documenting code. So I like the idea of introducing names, even when they're not necessary for the execution of the program, simply to show the reader, the uninformed reader, exactly what I'm trying to do. Now, you should always write your code as though you are writing for somebody who has never seen the code before to read, because you yourself will be that person in a couple of weeks. So you will remember poorly the exact motivation for why these things go. So it's always good to imagine somebody who's unfamiliar with the code reading it. If you would like to picture me looking over your shoulder, that's perfectly fine. But you know, be kind to your future self and try and make your code readable at all times. I would advise you not to do symbolic calculation inside of loops. Now what that means is we're going to be doing simulations of systems. We're going to be passing functions to integration routines, which will be calling those functions many times as the simulation progresses. If you are doing symbolic calculations inside of your integration function, your integrations will be slow. How slow? I'm trying to show throughout this notebook to give you an idea that there are actually two axes on which we evaluate these different methods. The one is ease of use, and I think because of the close match between the way you would kind of do things on paper using symbolic methods and SymPy, my experience is that most students have a very strong affinity for SymPy. So they lean very strongly in the direction of using SymPy because it makes a lot more cognitive, it makes sense to say, oh, I've made symbols, now Python knows about symbols, and now I can tell it to do math. That's a very easy thing to understand. Again, unfortunately, it is not necessarily the fastest way to do things. So we can see here that it takes a certain amount of time to find the solution. Now this is a linear set of equations, and one of the background themes of this module as we go through is that you will learn that there's a spectrum of difficulty in problem solving. Yesterday we spoke about level 0, level 2, and level 3 and so on of differential equations, but there's a kind of similar spectrum for algebraic equations as well. I think everybody can agree that a straightforward assignment kind of equation, x equals 5, must surely be the fastest kind of equation to solve, right? Because it almost doesn't require solving at all, right? X is equal to 5, there it is. The next level up is linear equations. So linear equations have this wonderful property that they are always solvable. So if I have any single linear equation, I can always solve, if I have a single unknown, I can always solve for that unknown in an unambiguous way. There's never some weird stuff where I'm dividing by 0 or anything like that. If it's a linear equation with one unknown, I just solve for that unknown and there you go. It turns out that systems of linear equations have the same property. So systems of linear equations are the best kinds of equations from a solving the equations point of view. If I can pose my question as a system of linear equations, I gain this amazing ability to solve those equations 100% guaranteed every single time using very, very straightforward and incredibly fast methods. So fast, in fact, that when we solve this as a linear system instead of as a general equation, you'll see that the solution time is about 10 times faster, or like an order of magnitude faster, to solve that linear set of equations. Now, it's still doing the same thing. It's still solving them symbolically in this case. So we're still using SymPy. If we solve those same equations numerically, and you must have, I hope most of you have come across most of the functions that I'm using here before. This should look familiar if you have done CBI. You've used this idea of solving linear equations before. Now I want you to notice that we're in the next order of magnitude in terms of speed, in terms of well, actually no, that's microseconds, right? So that's actually roughly 1,000 times faster. So what this means to you is, if you are doing simulations, we're going to be doing lots of simulations of our TC lab and a lot of different systems. 1,000 turns kind of seconds into days, right? So if you if you think about, there's about like in the order of magnitude of 10,000 or well 84,000 seconds in a day. And so if that's the kind of magnitude that you have, that's the difference between running your simulation and going to bed and coming back to it, and running your simulation and just immediately seeing the result and just getting on with your life. So this is the difference in magnitude that you could be seeing. Now, it's worth it if you're only solving one to gain that extra usability advantage, where it's maybe a lot easier just to write down the equations as they appeared in your book. The transcription is easier, right? But now you're leaving a lot of work to the computer, which means that the computer will take more work. This is not necessarily a big deal, like I say, if you're doing it one by one, but I'm going to show you the context within which we're going to solve these equations in a bit, and you'll see that we're going to be solving many of these equations many times. But we can clearly see that NumPy is very fast. Now, this is for a small 3x3 system. What if we do this for bigger systems? Now, recall, we've got 3 equations in our cup model at the moment, but if we're working with reasonably sized models, we're soon going to be working with 20s and hundreds and maybe thousands of unknowns that we're solving for. And so it becomes very important to understand how these things scale. Now, I'm going to build the same matrix. So I'm going to build a 30 by 30 random matrix. And when I do that with our linalg.solve, it takes 41 microseconds on average to solve that system of equations. So this is 30 simultaneous equations that we're solving. Now let's do exactly the same thing, but using SymPy. Okay, I'm going to keep talking while that happens. And I hope that this shows you, so here we can see, so that took a second. So that's 1 second versus 40 microseconds. Okay, that is roughly, seconds to days. And so if it could use, if it did actually use this much, if that was a second, this would be a day. We'd be sitting here running that for a whole day. Now, you can't outrun that speed differential quite as quickly as you would like. You know, so computers are getting faster, but they've stopped getting a lot faster. We're kind of at a couple of fundamental limits, so it's worth it writing proper code for this. So this is now kind of if I know that my equations are linear, or right up front, here I didn't need any assumptions at all. And so if you just want to kind of get a first cut at it, I would always at least start by trying to solve these equations. Also remember that if you solve that equation symbolically, like I have in the cup problem before, I can copy and paste the solution into my code, right? Because if I have a general solution and in symbolic form, that is the solution. So if I have a nice compact solution form, I can use SymPy once up front, copy and paste that equation that I've now gotten in. In fact, at that point, I've just used SymPy to do much quicker the solution that I would have done on paper to get to a general solution in my code. And in many cases, that can be faster. I say can because it's not always true. Right, so what about nonlinear equations? I must say SymPy is really quite amazing. SymPy.solve will be able to solve a large variety of equations. It is not true that SymPy will solve every single equation that you could solve. It doesn't necessarily know all the tricks, but in my experience, SymPy is at least as good as a third-year student at solving kind of relatively straightforward nonlinear equations like these ones. And you can see that it kind of also knows things about, it can solve, for instance, some transcendental equations. It can solve simultaneous nonlinear equations. That all works. So I think that would be a challenging problem for one of you to solve, right? So that's a simultaneous two equations. But SymPy can solve that really trivially in weird and unexpected ways. And this is like, I apologize for this, but unfortunately there is no general rule to determine whether an equation is solvable. So I think the basic idea is try it and see. And if SymPy can't do it, then we can resort to numeric methods. Now, the way that works, or the way that numeric root finding works, let me just get this. You have a relatively good idea of how numeric root finding works if you've done the numeric methods course. The methods that are used by the tools that we're going to be used map approximately to things like Newton's method. It's not guaranteed that it'll be exactly that kind of method, but the key idea of all numeric root finding routines is that as a general rule, they require an initial guess. And this is the first time that we've needed this. So if you look at the rest of the equation solving things that we've spoken about so far, at every time above this line here, we've just taken the equations and solved the equations. As soon as we have a numeric root finding routine involved, we will need to look at the starting point. This is because of a couple of different reasons. The first is that in general, you can't just look at an equation and kind of know what the answer is, because if you did, you'd just use that answer. Like, why are you using the numeric root finding routine? If you have a 1D equation, it's incredibly useful to plot it so that you can get an approximate read on where the root may be. I would recommend that if you are just coming across a difficult to solve equation and it has only one unknown, the first thing you should do is to try and plot it. Now, we can clearly see that there's kind of a root more to the left of 1 over there. And so remember, this was the equation that had a cos and a log and an x. And so if you think about the mechanics of solving these, you'd need to kind of, these kinds of equations are known as transcendental equations. They mix kind of sines and cosines and logs and so on, and normal versions of the same variables. And if you think about how you solve things with log by raising to a power, or how you solve things with a power by taking the log, you end up with this problem that if you're trying to raise the equation to a power to get rid of the log, then you end up with the x to the power. But if you then try and log that, you end up with the log again, right? So this is kind of a lot of times transcendental equations are effectively unsolvable by analytic means because you can't see a way to kind of get rid of all of those functions at the same time. So this is that unsolvable equation. We can see that's approximately where the root is. I'm using the built-in plotting functions over here. When we call plot without arguments, it just decides by some internal algorithm what the ranges are for things. We can tell it where x, or what values for x to use by specifying this range tuple. So we can say plot x from point 1 to 1. A common source of frustration with plot is forgetting that SymPy must have knowns for everything in that. So I can't plot a generalized equation like ax squared, for instance, if I don't know what a is. And you'll probably forget it at some point, and it'll say something about like undefined variable or something like that. Just remember that you have to have known values for all of the dependent variables that you're plotting for. Now, built into NumPy is a function called nsolve, which works exactly like solve. So solve attempts to solve systems of equations symbolically. Nsolve attempts to solve that same system of equations numerically. And so if you are starting in SymPy, you can easily find a numeric value by just using, like, just add an n in front, and basically that's the difference that you need to make. Now, it depends how we're going to use this. And it is incredibly annoying. I know this. I know it's terrible because it is an unfortunate protrusion of the implementation of these libraries into your mental model of how things work. But in general, you cannot pass SymPy things to the NumPy things. Okay, you really would like to think about it this way. You would want to say, well, I've defined here, it is mentally useful to say, here I have not created a list that contains a number of SymPy expression objects, which is kind of how I would describe it on the Python level, right? How your brain would like to think of this is, I have defined my equations in this line, right? I think most people are thinking of that and like, here is how you define your equation. Here is how you tell SymPy what the unknowns are. And here is how you tell it to solve those equations. Now, if you don't have that extra layer, if you don't remind yourself that this is actually a list of SymPy expression objects, you may be tempted to pass that set of equations to SciPy.solve or SciPy.optimize.solve. Okay, because if your top level mental model is, I have defined equations, then it makes sense that I can pass those equations to functions that solve equations, right? If I have, here's a couple of functions that solve equations, here's how you define equations, you pass the function to the thing, and they solve equations. Unfortunately, this is not true. SciPy and SymPy know nothing of one another. So there is no attempt by the SciPy people to interoperate with the SymPy people. These are completely different sets of developers. They have their own goals. They have a whole set of objects that are completely different between them. And so in general, I would, every single time I pass a SymPy thing to a SciPy thing and it works, I am surprised, not the other way around. And you will initially have to fight your surprise at that not working, if you live on the high level. So as long as you look at this and remember, this is a Python list, not a set of equations. And that Python list contains SymPy expression objects. And so why would the SciPy library be able to call that? Now, the SymPy people at least understand that in many cases we want to follow the path that we're going to follow now, which is to start with symbolic calculations, do some manipulation using SymPy, which is allowing us to rearrange equations or solve for unknowns or whatever, but eventually we would like maybe to do numeric calculations using the well-established SciPy and NumPy libraries. Now, in order for that to work, the SymPy people have supplied us with this wonderful thing called LambdaPhi. Now, LambdaPhi is poorly named if you have never in your life come across the Lambda keyword in Python, because then you don't know what that could possibly mean. So I just want to also show you what the Lambda keyword in Python does. The Lambda keyword in Python allows you to define a small anonymous function. So what I have done here is I have created a function using the Lambda keyword. This is, from a functional point of view, exactly the same as doing this. So this line and those two lines, from after I've executed those two lines, I would have had something that is quite similar. In other words, a function that adds 2 to its argument. So if I do it over here, so if I just execute this and I do +2, just to show that it works, that's what happens. Okay, so the Lambda keyword introduces these functions. They are called anonymous because they are not given a name. I don't have to give it a name. So if I just execute that line, what I end up doing is just building the function, but it doesn't actually have a name. I can obviously assign it to a name, or I can reference it using a name using equals, just like every other Python function. Yes?
So what would happen if you define two variables? Would you just say lambda x, y, and then you would just...
Yes, you can. I mean, you can pass in an arbitrary number of variables. So
and then just consider 2, 2 at the variable or function name. When you call it.
Yes, it works just like a function. Yes. Now, I'm not going to go into a great deal of detail into how Lambda works because I strongly discourage you from using it. As does Guido van Rossum, the creator of Python. I'm showing you why LambdaPhi is called LambdaPhi. I'm also showing you, just in case, because you will come across in the wider literature of, so there is literally, in Python, there is no reason ever to use Lambda. There's no special stuff that only Lambda can do that you couldn't equally do by defining a function. So my very strong advice is to avoid the Lambda keyword when you write code. It is important because you'll see many references to Lambda in documentation. So it's important to be able to read it, but it's also important to avoid writing it. Okay, so this is so that you understand what it means, but I advise that you don't actually write those functions yourself. Yes?
With something like solve IVP,
yes.
Lambda is very useful because solve IVP doesn't have the args keyword.
No, there's no reason to use it. You just define a function. Just define a function. When you think you need Lambda, just define a function. So why it's called LambdaPhi is a reference to this. Lambda is a way of turning an expression into a function. Okay? So just to be clear about the words that I'm using here, this thing which colloquially your brain is thinking of as an equation, right? From a computer science point of view, and the words that SymPy will use when talking about this object is that this is an expression. So an expression is, and this is the same nomenclature that's used, by the way, by the Python documentation. So it's everything that is a valid right-hand side for a Python assignment is an expression. Does that make sense? So everything that you could possibly successfully write on the right-hand side of equal sign in Python is also called in Python an expression. Now this is a symbolic representation of that expression. It doesn't by itself do things. In other words, I can't do that. I can't call that expression with a value for x. It is just an expression which does by itself not actually do things. I can substitute, so I can evaluate that expression at a particular point by substituting a value for x. But it's not the expression that's kind of actually doing the work itself. Doing this allows, at this point, unsolvable numeric is a function, or at least behaves like one. So I can call it with a numeric argument and get a numeric answer back. This is very useful because it allows me to use fsolve, which I'm sure all of you have come across before, so scipy.optimize.fsolve. This is, in SciPy, the numeric solution routine. So in SymPy there is nsolve, and in SciPy there is fsolve. The fsolve routine works only for numeric values. There's no way to handle symbolics. But this is the bridge that bridges us from SymPy to SciPy. We don't need a very good bridge the other way because nothing that SymPy or that SciPy produces is symbolic, right? Because SciPy always just is numbers. It's much less of a big deal to go from SciPy back into SymPy. But we always have a problem because we have symbolic stuff in SymPy and we'd like to do it numerically in SciPy. The context of this for our cup simulation, it becomes progressively more difficult. I've been playing around with different data files. It becomes progressively more difficult to retain everything symbolically when we're working with expressions like the expression that we have that relates height to volume in our cup model. You'll remember in a previous lecture I showed the particularly hairy solution for trying to solve for height given a volume, right? Remember that the volume is a ternary or a third order polynomial of height, which means if I'm trying to solve for height, it becomes very, very hairy very quickly. However, it is actually a lot easier to solve if I'm solving numerically. And so I'm going to show you this approach. This is the last little bit. I'm almost done. So you'll recall this notebook where we were plotting the volume and height of our cup experiment. So we're taking exactly this model. And in a previous version of this, we used this very simple way of kind of approximating what the k value would be. We just back calculated it. In my experience, I've used this because in something like 7 years of working with laboratory experiments in CLB, I know that this is pretty much everybody's first instinct at estimating k. I think most of you didn't even think about why I was doing it this way because it's the quote-unquote obvious way to do it, right? So if I have an equation like this, I've got fh is equal to kh. I can solve each row in the Excel spreadsheet for k. And what's a good estimate for k? Oh, it's the average value of k. Job done, no problem, okay? Except two problems, two very important problems. This doesn't work when h becomes 0, because that means I have to divide by 0, so that's a big problem. Turns out it's also not a particularly good fit visually for what the actual line looks like. So when we plot this, we see it seems quite far away from those dots, the line that we're fitting. Now we can do a little bit better by actually fitting a curve using SciPy curve fit. Now you can see here, I've defined a function to fit to this data. In SciPy optimized, there's a curve fit function which allows me to fit the curve. This is basically the same as the line that you would get if you fitted a regression line in Excel. Notice that it is different from the one that you get by taking the mean of the k values. It's a lot better, in fact. Well, I think everybody can agree that that goes a lot closer to all the points. Then, and I'm going to be uploading this as well, then we want to solve the draining problem. So I've defined here a function which allows me to calculate the h given the volume. And this is where your lambda would have come in, right? So I've just defined a function for the residual which takes my pre-calculated volume and subtracts it from the given value. So that's the residual. I've used SciPy.optimize.fsolve to solve for the height that makes that equation true or makes that residual 0. And that's kind of giving me a function that allows me to get height from a volume. I've defined, by now this should be familiar to you, I've defined a function that returns the derivative. I've called the function that I defined earlier, and that's what those results end up looking like. So it's not that bad. We can experiment with different kind of functions to do this. You'll see in the final notebook that I'll upload a little bit later today that I've already done this. Here's one that I prepared earlier, as they say. And I've done that, copied and pasted everything, and calculated the k value and plotted it as a function of the whole height. So reassuringly, the k value becomes bigger as the whole becomes bigger. But it looks like we're still missing a little bit of information there. But I hope that gives you a context of what the tools are that we have for solving equations, why we're solving equations in the first place instead of just rewriting our equations so that we can run them all the way through.